Okay, so welcome back, and this is the last video in the section looking at atomic structure. So in this video we're going to be looking at mass spectroscopy. We're going to be focusing on the mass spectra of elements. In a later topic you're going to be studying the mass spectra of molecules, looking at their fragmentation patterns. But for the moment we're just going to concentrate on elements, so you're going to need a calculator and you're going to need page 14 of your notes. So in your notes you should see this basic diagram of a mass spectrometer. You don't need to know in-depth details of how it works, you just need a very basic understanding. So firstly of all, we're going to vaporize our sample. Then once our sample has been turned into a gas, we can ionize it. We ionize it by hitting our sample with a high energy electron. This knocks an electron off of the molecule or atom, giving it a positive charge. We then accelerate it by using an electric field. We can then move on to deflecting it using a magnetic field, and last but not least, detecting via an ion counter. The important bit to notice here is that you have to hit it with a very high energy electron to turn it into a positive ion. So all the species detected in a mass spectrometer will have a positive charge. So you have to remember a mass spectrometer is used to weigh atoms. Now because isotopes will weigh different amounts, we'll get different peaks on our mass spectra. So here is an example of one. Up the side here I have a scale of relative abundance. The value along the bottom is what we call the MZ value. So that is the mass divided by the charge. For our purposes, we're only at the moment going to be considering ions with a +1 charge. So that would be the mass divided by 1, which will just give us the mass. And you can see here I've got two peaks. I've got a peak at 10 and a peak at 11. The reason I've got that is I have a sample of boron here, which has two isotopes, boron 10 and boron 11. The other piece of information I can tell from this spectra is I can tell that the boron 11 sample is much more common than the boron 10 because it's got a much higher abundance. So I can see that boron has two isotopes because I've got two peaks on my mass spectra. It tells me that they have mass numbers of 10 and 11. And from their relative abundance, I can say that there are 23 boron 10s for every 100 boron 11s. And I can use that to calculate the relative atomic mass of boron. So I can work out my relative atomic mass of boron by saying I've got 23 out of every 123 is boron 10, and 100 out of every 123 is boron 11. And if I do that, I get a 10.8. Now that is the relative atomic mass of boron. If you think back to your definition, it was the weighted average mass. This explains why some of the elements on the periodic table have a decimal place for their relative atomic mass number. Because you have to remember it's the weighted mean mass. So it's the average mass of all the isotopes. So we're on page 16 and we're going to be looking at the mass spectra of bromine. So bromine has two isotopes, bromine 79 and bromine 81, and they're roughly in the abundance of 50-50. So bromine can exist as atoms, but it more normally exists as a bromine molecule. Now there are three ways I can get a bromine molecule. I can get a bromine 79 atom joined onto another bromine 79 atom, or I can get a bromine 81 joined on to a bromine 79, Or I can get, last but not least, a bromine 81 joined on to another bromine 81. So you can see from here I'm going to get molecules with 3 different masses. And the idea of a mass spectra is that it weighs atoms or molecules. So these 3 molecules, although they're chemically identical, they're going to weigh slightly different amounts. And here are my 3 different amounts: 158, 160, 162. So I'm going to get these lines on my mass spec representing the molecules. Now, do remember that this is a mass spec, so each of these also has, probably better put it there, has a positive charge on it. And I'll show that a bit later on. But each of these, somewhere, I've got to stick a positive charge on it. Otherwise they won't go through the mass spectrometer. Okay? So we have the bromine 7979, which adds up to 158. We have a bromine 7981, which is 160. We have bromine 8179, which is again 160, and we have bromine 8181, 162. So there I have my bromine molecules. So I have a 7979, which adds up to 158. I have a 7981, an 8179, and an 8181. So you can see there I've got 2 160s, 1 158 and 1 162, and this is going to help me when I come to draw my mass spec chart. So the first thing I'm going to draw on my chart is 2 peaks to represent the 2 atoms, and you'll notice those peaks are roughly the same height, and that's because I have the same abundance of 79 as I do 81. So that is 79, that is 81, so this is a bromine 79 isotope, don't forget the positive charge on it, and this is a bromine 81, again with the positive charge on it. And then I have my 3 molecular ion peaks, and they are on the ratio 1 to 2 to 1. So I'm going to draw those on my chart. Probably use centimetres, might be better. So I've got a 1 to 2 to 1 ratio. So that is my 158, my 160 and my 162. So this one will be my bromine 79, bromine 79, don't forget the positive on that. And there I have my other molecular ion peaks as well. So I've got 3 molecular ion peaks in total in the ratio 1 to 2 to 1. And I've worked that out doing this little chart here. So the last bit on this page 16 asks us an exam question which caught out a load of students when it was asked a few years ago. So mass spectrometer was used to analyse bromine. We've only got the bromine 79 and 81 isotopes. Why do we get a peak at an MZ value of 80? Well, we have to understand what this MZ value is. It is the mass to charge. So it is the mass divided by the charge. Now in all of these cases we've only got a 1 plus charge, but there's nothing to stop us getting a 2 plus charge. So if we had a bromine 81, bromine 79, but this time with a 2 plus charge, the MZ value would be 81 plus the 79, so the mass divided by 2, which would give us a mass of 80. So we're now going to look at the mass spectra of chlorine. So we've got our chlorine molecule. It can ionize in our mass spec by hitting it, remember, with that high energy electron. It will knock off an electron to become a positively charged ion, and we will get that electron left over. Now, chlorine has 2 isotopes again, 35 and 37. This time it's in a 3 to 1 ratio. So I'm going to get 3 times as many chlorine 35s as I am a chlorine 37. So just like I did for the bromine, I'm going to just fill in this table. So I've got, as I said, 3 times as much chlorine 35 as I've got chlorine 37. So that means in terms of the molecules, I'm going to get 9 chlorine 35s to every 6 chlorine 35s 37s to every 1 chlorine 37. So my chart needs to look in the ratio of 9 to 6 to 1. So I have the ratio 9 to 6 to 1. So 9 out of every 16 molecules will be 35. And I can work out then the percentage abundance for each of them. So I can work out my percentage abundance, and that will help me when I come to draw it onto my mass spectra chart. So I'm going to draw my 2 atoms first of all, and they're in a 3 to 1 ratio. So I've got a 35 and a 37. So that's my chlorine 35, and it's 3 times as abundant as my chlorine 37 is. In terms of my molecules, I've got a 9 to 6 to 1 ratio, or 56% to 37% to 6.25%. So again, I'm going to do them in roughly the right, I'm just doing a sketch graph, but it has to be reasonably correct. So I've got them in a 9 to 6 to 1 ratio. You don't have to be exact on this, but you do need to show that they are roughly that ratio. So there I have my completed mass spectra for chlorine. I've got my 2 chlorine atom isotopes, and then I've got my 3 molecular ion peaks in the right ratios of roughly 9 to 6 to 1, and this one in the ratio of 3 to 1. So it's important that you show the positive charges, and it's important that you show the relative or percentage abundances. So the last type of spectra we're going to be looking at is whole molecules. Now we're going to be studying this a little bit later, but you've got molecules here, for example, of water. Now when you put this through a mass spec, sometimes it will do what we call fragmentation. In other words, it will break up into different bits. But there'll usually be one ion, this one, which has the largest MZ value, or it's the line furthest to the right hand side. And that gives us one very important piece of information. It gives me the mass of the ion, it gives me the mass of the molecule without being broken up. So the mass of the molecular ion peak is 18, the molecular ion is H2O positive. The next example is an organic compound called pentan-3-one, and the molecular ion peak is here. This is 86, and that is the mass of the molecule. So that's CH3, CH2, CO, and then another CH2, CH3 positive. So that's the mass of the molecule. And the last one is here, 72. Remember, it's not the most abundant peak I'm looking for in this case. It is the one with the largest MZ value, because that gives me the mass of the molecule. It gives me the RMM of the molecule. So here the RMM, or the mass of the molecular ion, is 72, and that relates to this compound here, pentane. And there's my pentane molecule. And if you add all of those up, you'll get back to 72. Okay, so that completes the first pack of your notes. So using the video and your lessons and the PowerPoints, you should now have completed all the exercises in the pack, and you're ready to start the questions at the end. So these are exam questions taken either from AS or A-level papers over the last few years. Have a go at them, then we'll ask you to hand in the pack. We'll mark it and give it back to you. At that point, you'll need to correct your answers using the mark scheme on GOL. And if you've got any questions, speak to one of us in the lessons, or you can always come along to one of the chemistry clinics. They're on Fridays and Tuesdays after college. So until then, stay safe. Speak to you soon. Bye bye.